Hey, what's up everybody, and welcome back to Quantum Mechanics for the Working Professional. Today we're going to be doing another problem solving session, specifically devoted to the first few problems of section 2. More precisely, we're going to be looking at, problem 2.1 and 2.4 and 2.5 altogether. Regardless, what we are going to be doing actually is computing the expectation value for two spin operators, spin in the z direction and spin in the x direction. Additionally, we'll also compute the variance of those two operators. So let's get started. First, we begin by reminding you that the quantum state, the generic quantum state that we'll be considering, is psi, which is parameterized by two numbers, alpha and beta, alpha up plus beta down. We can write this in column vector notation by simply writing alpha beta. The two operators, that is to say matrices that will act on this column vector state, are Sx and Sz. So Sz is hopefully familiar from lecture, and that is just h bar over 2 times 1, 0, 0, minus 1. Sx, the spin operator for measuring spin in the x direction, which you can think of as doing a Stern Gerlach experiment where you take that big honking magnet and you rotate it by 90 degrees into the x direction. That is also represented by a matrix, and that matrix has a similar form. It is 0, 1, 1, 0. Still, of course, multiplied by h bar over 2. So you might recall that the expectation value of an operator is given by psi, let's say Sz psi, over the inner product of psi with itself, right? That is the that is the expectation value of S sub z. Now we'll be assuming that psi is, for all intents and purposes, normalized, so we're going to take it to be equal to 1 in this case, so that really we only need to compute the inner product of psi with itself with an operator sandwiched in the middle. So let's go ahead and do that. We'll do that for both cases. For Sz, hopefully the answer is familiar. So we have alpha and beta. Then we have that operator, 1, 0, 0, minus 1, and alpha and beta column vector. Of course, we forgot h bar over 2 on the outside. This is the expectation value of S sub z, right? So we can compute that constant value, just pull it out in front, and then we'll still have alpha and beta. Now we will multiply the vector, the column vector, against the matrix and see what we get. So 1 times alpha, 0 times beta gives us alpha, and then 0 times alpha and minus 1 times beta gives us minus beta. This is hopefully familiar from lecture. So this is just h bar over 2 times mod alpha squared minus mod beta squared. Again, just like we saw from lecture, the purpose of these exercises is to have you do them so that you can make sure that you know what's going on. So consider this a bit of a review. Now, let's do the expectation value of Sx. Similar program. We're going to pull that h bar over 2 out front. We'll have the alpha and beta, and then we'll have that matrix 0, 1, 1, 0, and then alpha and beta. On the outside again, computing, we find that the funny structure of that matrix associated to the Sx operator gives us 0 times alpha plus 1 times beta, so that's beta upstairs, and 1 times alpha plus 0 times beta, so that's alpha downstairs. So it had the effect of flipping alpha and beta in the vector. So now we can complete our little calculation here, and we find that that's alpha beta plus alpha beta, or 2 alpha beta, right? So h bar alpha beta. The pendants in the audience will probably want to say something about complex numbers and the complex conjugate. And yes, we are going to get to complex numbers in section 3. We're not quite there yet, so we're still assuming that alpha and beta are given by real numbers, so we don't have to worry about Hermitian conjugates and all that kind of stuff. We'll get there. But for now, it's suffice it to say alpha and beta are just real numbers, so everything is fine. It's not as complicated as it you might worry that it is. So great, we have the expectation values for Sx and Sz now. Okay. Let's remind ourselves what the formula for the variance is. So the variance of an operator, say O, is, well, in quantum mechanics language, we usually represent it by this little triangle here. So triangle O is given by the expectation value of the operator O squared minus the square of the expectation value of the operator O, right? Okay, so for the case of Sx, that's just going to be the operator Sx squared minus the expectation value of x, right? Good. Okay, you know the drill. So what we need to do in order to compute the variance of sx and sz is to compute the expectation values of these operators squared. So let's go ahead and do that. First, we need to know what those operators look like when they're squared. So sz squared we did in lecture, so let's just quickly review it. That is h bar over 2 squared times 1, 0, 0, minus 1, 1, 0, 0, minus 1, right? So that's h bar squared over 4 times, quick computation, that's a 1, that's a 0, that's a 0, and that's a 1. So as we saw in lecture, that's h bar over 4 times the identity matrix. In other words, just 1, basically. Super easy. Okay, so that tells us right away, by the way, that the expectation value of s sub z squared is just h bar squared over 4 times psi 1 psi, and the identity matrix is, in some sense, trivial. And additionally, since we're assuming that we're using normalized states, that's just equal to 1. So in other words, the expectation value of SZ squared is just h bar squared over 4. Piece of cake. Okay, let's now compute the expectation value of the operator Sx squared. So to do that, we need to know what is Sx squared. Similarly, it's just h bar over 2 squared times 2 copies of that matrix. So that's 0, 1, 1, 0, 0, 1, 1, 0. Right, so now we can compute. So that's h bar squared over 4. Again, times now 0 times 0 plus 1 times 1 is 1. Da 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 da, 0, 0, and look at that, 1. Again, we get h bar squared over 4 times the identity matrix. So in other words, as was one of the questions in one of the problems, you've just shown, or we have just shown, that sx squared is equal to sz squared. So in particular, the expectation values of those operators in the same state are also equal, and they're both equal to h bar squared over 4. Right, so that doesn't mean necessarily that the operators are a priori equivalent. What it means is the matrices that represent sx and sz are equal. Easy. Okay, good. So now let's go ahead and use all the facts that we have now to compute the variance of both operators. So the variance of sz is going to be given by this familiar term, which is just, as we learned, h bar squared over 4 minus h bar over 2 mod alpha squared minus mod beta squared. But then we need to square that whole thing. Good. Now, in the hint associated to this particular problem, I asked you to assume that alpha squared plus beta squared is equal to 1, right? And insert basically, or the hint was that 1 squared is equal to 1 as well, right? So what we're going to do is just insert that here. And so we have h bar squared over 4 times mod alpha squared plus mod beta squared, which is 1 because we're using normalized states. And I'm going to square that because 1 squared is squared, still 1. And then we can subtract the second term, which is very similar except for this minus sign. And what that tells us is that only the cross terms are going to contribute from all of this mess, because things that look like alpha to the 4th or beta to the 4th are going to cancel. And so what we're left with is, this is very straightforward, h bar squared over 4 times the cross term of the first term, which is 2 alpha squared beta squared, minus a minus 2 alpha squared beta squared. And so we're left with h bar squared alpha mod squared beta mod squared, since the 4 cancels out, as we had in lecture. Great. Okay, so now let's go ahead and compute the variance of the Sx operator. So this is somewhat similar in the sense that we've got h bar squared over 4 again, but now we have to subtract off h bar alpha beta, whole thing squared. Okay, so this gives us h bar squared over 4, which I'll factor out of both terms, leaving us with 1 minus 4 mod alpha squared mod beta squared. Right? Good. So what does that tell us? Well, it tells us, first of all, that that's the answer. Okay, so good. There we are. It might be useful to now do some case studies and see what's going on. Okay, so let's go ahead and do that. So for the expectation values, let's look at the different spin cases that we've seen so far. So spin up, right, was alpha equals to 1, beta equals to 0. We learned that the expectation value of spin up last time is just given by up, sz, up, which is just h bar over 2. In the case for sx, which is of course given by h bar alpha beta, that's h bar times 1 times 0, so it's 0. The expectation value of the spin up operator, the expectation value of sx, the spin in the x direction of the spin up operator that we've been, or the spin up state, start over. The expectation value of the spin x, the spin in the x direction operator for the spin up state in the, from the Stern Gerlach experiment that we've been discussing is 0. And what that means is, and as we've already seen, what that basically means is that the measurement of spin in the x direction is equally distributed between spin up or spin down. Whereas in the z direction, we know precisely that it's going to be spin up. And so the expectation value is precisely h bar over 2. Similarly, in the spin down case, when beta is equal to 1 and alpha is equal to 0, we have once again h bar times 1 times 0 for the expectation value of the spin in the x direction. So once again, that is 0. And here, of course, we have just minus h bar over 2, right? Because sz on spin down is minus h bar over 2 times spin down. Great. Okay. In the solutions to the problems from last time, we also studied different states that are worth exploring as well. So let's consider the state where alpha is equal to beta. If alpha is equal to beta and alpha squared plus beta squared equals 1, this implies that alpha is equal to beta is equal to 1 over the square root of 2, right? So what does that mean? So that means that the expectation value of sx is given by h bar times 1 over the square root of 2 times 1 over the square root of 2, which is just h bar over 2. So that state that we call, like phi 1, or like the normalized version of phi 1 tilde, the expectation value of sx in that case is just, right, h bar over 2. Similarly, the expectation value of the orthogonal state that we discovered, right, in this state is given by minus h bar over 2, right, because that's going to be h bar times 1 over square root 2 times minus 1 over square root 2. Cool. So what we've learned is that phi 1 and phi 2 are actually a better representative for measuring a particle that what we've learned here is that that these states phi 1 and phi 2 are tuned, if you like, precisely for measuring spin in the x direction. And we'll talk a little bit more about that when we talk about some of the other problems down the road. But for now, let's just quickly cover some more details about the variance. Let's do those examples again for the variance. Right, so let's organize it this way. We're going to be talking about the variance S sub x and the variance S sub z. And we're interested in now 4 states. This is the spin up state, the spin down state, the phi sub 1 state, and the phi sub 2 state. Okay, so we saw that the variance of SZ is given by h bar, what is that? That's h bar squared times mod alpha squared mod beta squared. So for the case of the spin up operator, that's going to be 0. Why? Because beta is equal to 0. Did I say spin up operator? I meant spin up state. You know what I'm talking about. Good. Similarly, the variance for the spin down state is also 0 because alpha is equal to 0 in this case. So just what we've learned, there's only 2 options for measuring states spin of silver atoms, right? It's either up or down. So if we have an expectation value and we know precisely that it's going to be in the spin up or spin down state, if the expectation value, if you like, is non-zero, it's not one of those 2, then the variance necessarily must vanish in those cases. right? Why is that? Because there is no variance. The variance in some sense measures the superposition of a state between two orthogonal states that we can measure. Okay, so now let's ask the same question, but of the spin x operator. So remember that this was something complicated. It was h bar squared over 4 times 1 minus 4 alpha beta squareds. Okay, so in both of these instances, for the up and down states, we either have alpha or beta equal to 0. So that second term that we discussed also vanishes. So in both of these states, the variance of the spin x operator is h bar squared over 4. And that makes sense given what we were just talking about, because the expectation value of the operator Sx in the spin up or spin down state is 0, because when we're measuring, remember, these spin up and spin down states that we originally were talking about were actually originally tuned to the Stern Gerlach experiment when the magnet was facing the z direction. But now that we've rotated the magnet, those states are no longer tuned. Our basis is no longer correct. So now we need to find a different basis to make things more straightforward. But regardless, the expectation value of either state, up or down, is 0, because it could be either or, 50-50 chance. But that means that the variance of either state is maximal in the sense, at least for a one particle state, which is h bar squared over 4. So now let's go ahead and do the same thing for these other states, phi sub 1 and phi sub 2. So the variance in the x direction of phi sub 1, right? So alpha, remember, this is where alpha is equal to beta is equal to 1 over the square root of 2. So that means that whatever it's going to be, h bar squared over 4 times 1 minus 1, right? Which is, in other words, the variance is going to be 0. And similarly, since it's mod alpha squared and mod beta squared, for the case of psi 2, where alpha is equal to minus beta is equal to 1 over the square root of 2, right? This will also be 0. And this is consistent with the fact that the expectation value of these of the operator Sx in these states is given by either h bar over 2 or minus h bar over 2. In other words, it's precisely known. So once again, if the state is precisely known, its expectation value, if the state is precisely known with respect to that operator, its expectation value is non-vanishing, in some sense is maximal, right? And if that is the case, then there is no superposition. And if there is no superposition, that means there is no variance. But let us now compute the variance of these states in the z operator, right? Where alpha, which is just proportional to mod alpha squared times mod beta squared. So in this case, it's going to be h bar squared times 1 over the square root 2 squared times 1 over the square root 2 squared, which is 2 squared, which is 4. Which is, again, in some sense, maximal. Because once again, we don't know how the state phi 1 will react if spit through the Stern Gerlach device in the z direction. Similarly, because again, once again, just mathematically speaking, it's mod alpha squared, mod beta squared, we have exactly the same number. So you can see the parallels here. And so once again, really what we've done here is found a basis of states that reflects the Stern Gerlach experiment if we rotated the magnet in the z direction. So I'll finish it up here by saying one final fact, and we'll get back to this when we study some of the other problems. And that is that if I had the Stern Gerlach device, right, if I had that little oven that took silver atoms into a little beam, and I measured, instead of the z direction, if I measured the x direction, what that tells me is that the state coming out here would be phi 1. And the state coming out here would be phi 2. That's the nuance. If, we were measuring in the z direction, of course, which is like how we had it in lecture, then this would just be the spin up state, and this would just be the spin down state. Okay, great. That's all for these problems. Hopefully that was a good set of arithmetical exercises that maybe explained a little bit, or at least hinted a little bit at where we're going with all of this. Next time we will review some more problems, I suppose. Okay, great. So see you then.